So this OSI model, which is defined, the different layer, 7-layer model defined by the International Standard Organization for any communication network, including optical communication network, is the following. So the entire network functionality is divided into 7 layers, of which the top 3 layers are actually at the higher level layers. So let's say we are trying to send an email from my computer here to let's say to somebody else. Let's say I'm sending an email to you, which you will be reading again as an email. So the top layers talk about the end user processes. So if I'm writing an email, I would be using email server, I would be probably using a browser, or if I'm searching, I'll be using an HTTP and so on. So those are your, applications. So this layering is done based on the functionality, and the top, the application, the presentation, and the session layers take care of the front end user processes. It also takes care of coding and encryption. So when I'm writing an email and it gets coded into something, it gets encrypted. For example, if it's a picture, you have a JPEG or an MPEG kind of encryption, the authentication of that, the permission for that, all that is done by the top layers on from the source as well as in the receiver. So in this, from the transmit data, it goes through all these layers down all the way up to the physical layer, and in the receiver it goes all the way back to this, right? So once I send an email, the top layer functionalities gets done, it goes down, finally it becomes an electrical signal, and from electrical signal it gets converted into an optical signal, finds its path to the geographical location where I am trying to send it to, and there it goes back from an optical to an electrical signal and goes up in the layer and finally becomes an email at my receiver. Followed by this top 3 layers, you have error control from end to end, which establishes the path and says that, okay, there is no error in transmission from user A to user B. So that is taken care by the transport layer. So it establishes the end-to-end communication link with the error correction management. And then, of course, the routing, the switching from one node to the other, deciding the path, etc., that is done by the network layer. So all these are in the software. Okay, all these are not in the hardware. This is all in the software. Data link layer is the one which is partly in the software and partly in the hardware. We will see the details of that. So the flow control in the physical layer is done by the data link layer. The data link layer is also involved to some extent. We will talk in detail about data link layer, but it's involved in some kind of multiplexing the data. And the last, the bottom layer, is the physical layer, where your information is in the form of bits. The physical medium in a traditional communication system, in a wireless communication system, it is in its atmosphere, whereas in an optical communication system, it's of course the optical fiber. So all our transmitter, channel and receiver, which we were talking about in the previous sections of the course, are physical layer aspects. Above that, you will have the data link layer, which basically frames the information. So some amount of regeneration, etc., happens in the data link layer. And then above that is all in the software. Okay, let's talk about the physical layer now. So the physical layer, in case of an optical network, it has basically 2 parts. One lower layer, which is the fiber infrastructure, the actual fiber that is laid on the ground. So you have the fiber link, which is shown in yellow here, that is laid in either as a submarine network or as a terrestrial network, or it could be on your OPGW cables, it could be on the electrical cables, the ground cables which carry the ground cables corresponding to the electrical power connection has optical fiber in it for the purpose of communication. So this it could be in the optical, it could be in the electrical power cables also. Okay, and there are these optical nodes, and some of the functionalities of the optical nodes we have already seen. It could be in add drop multiplexing, it could be in optical add drop multiplexing. In fact, we talked about a reconfigurable add drop multiplexing also. Above this fiber infrastructure layer is the physical optical layer. Now this optical layer actually provides the light path in the sense that it ensures end-to-end optical connectivity. So this is the point. For example, you could have data in the electrical domain which gets converted into the optical domain and passes into your optical layer. In case of a WDM system, the channel selection, etc., will happen in your optical layer. So one is the physical fiber infrastructure. Just above that is where your O2E converters are sitting, and that's where your path, the wavelength and the path gets decided. So all these transceivers are sitting in the optical layer. And above that is, of course, all your other layers which are riding on the from data link layer and which are riding on the software. Okay. Now, what about the data link layer? Now, the data link layer is the key part which links or which enables the data to be understood by the software, the network management system. And the way it connects to the lower layer is such that it provides bits which needs to be encoded in the optical to electrical, in the electrical to optical converters. So what it does is it basically makes frames of information. Now, what does this frame contain? The frame contains the header, which tells the source, the destination, the priority, the type of formatting, etc. Right? So the protocols, etc. So it has the header, then it has the packet. This packet will have the actual data that needs to be transported, and it also has a trailer information. So you know that for a fact that all the optical communication today is carried out as digital communication. So the packet will carry ones and zeros corresponding to the data, the digital information corresponding to the analog data that you want to transport. The header will consist of all this information on where this data has to be sent, and let's say I'm writing an email, and so this basically takes the from the application layers, it actually pulls out the address and it tries to put in something which tells the network where this information has to get routed. So it basically makes sure that there is a seamless communication, or it's a seamless way of transferring information from the physical layer to the data, the software layer above, and from the software to the physical layer below. So the data link layer basically enables the what the software requires to be transported into the physical layer and back. For example, the communication network can get established between different physical layers. It's not necessary that it's only between a fiber to a fiber the link is getting established. So what the data link layer is going to do is to make sure that the network gets established between the different physical layers, even though the channel could be completely different. For instance, you could be sending information from an antenna to a satellite, and so your information should get framed such that it is going through your satellite communication and it gets back to your physical layer. So the bits, as we said, which is the information that needs to be transported, it gets converted into frames, and the frame will identify the network layer protocols, the different protocols, and the standards that are specified. Again, the protocols, the way you are mentioning the source and destination also should form a certain rules, and this set of rules is what is referred to as protocols. And these protocols are standardized by either ISO or IEEE or ANSI or ITU. In this, the ITU is the one which gives the protocols for optical communication. Okay. So, for example, the protocol can be such that, you know, you are trying to establish connectivity from, again, take the example of sending an email from a source to a destination. You may be connected through a wireless router. So, initially it gets framed through this particular protocol. It could then get converted into point-to-point protocol which provides this connectivity, or it could get, so HDLC is the name of another protocol, networking protocol that is being used, the layer 2 protocol that is being used. You could then probably, the receiver computer could be connected through a Ethernet connection. So, the receiver computer now needs to see an Ethernet frame. So, the data link layer of this particular router, at that point it will actually convert the frame to an Ethernet framing, and then you get to your destination. So, these are several examples of the different network protocols that are used in layer 2. So, now we will see that there is a slight departure from the 7 layers that are given by OSI in case of optical communication. So, all this layering was done on the basis of traditional wireline wireless communication systems, but in optical communication systems we know that the fiber can provide a really large bandwidth. The physical layer can provide really wideband transmission. So, a specific user data, we talked about transferring information from user A to user B, but that data could be the rate at which the user generates the data, and the receiver B is, user B is ready to receive the data, that could be very small as compared to the information carrying capacity of the fiber. Right. The fiber, we have seen that it can carry really large bandwidths. You are talking about 100 gigabits per second and so on. But the cell phone that you have, or the Ethernet router that you have, it cannot process data at 100 gigabits per second, right? So, what really happens? Even if you want to try to send your voice information, the data rate required is not very large, or rather the users do not require individually that large data rate. So, there must be some functionality in the network that is aggregating the data from different users, multiplexing them, and then transporting them through the different parts of the geographical network, and similarly deaggregating at the receiver side or at different nodes. So, that brings in different layering, a slightly different layering in optical networks, and the corresponding standards are known as SONET, SDH and IP. We will talk about that in detail. So, the new layer is called as a client layer, and this client layer we will try to fix it within the optical layer, because we do not really want to disturb the entire layering system. So, what does this client layer do? It will try to aggregate the different low speed data streams. Remember, this happens in the electrical domain, not in the optical domain. Even though we say it is within the optical layer, remember in the optical layer there was a fiber infrastructure, and there was an upper layer which was having partly electrical, and then you had transceivers. So, this client layer sits above the transceivers, which means that the client layer still handles the electrical information. So, it aggregates the different low speed data streams. It is packaged in a certain format. It is multiplexed with different users, and then you can, the aggregated data rate now becomes really large, and hence you can utilize the entire bandwidth of the fiber. So, again, this needs to be done in a very standardized manner. I mean, I cannot do it one way at the transmitter and another way with the receiver. It has to be, the same language needs to be spoken by the entire network, and that standardization is your SONET and SDH. So, SONET stands for Synchronous Optical Network. It is a multiplexing standards. It actually developed in North America. Parallelly, SDH is a similar set of rules, and that's a standard that started getting used in outside North America. So what is done currently is that it is tried to we try to make sure that the total frame size, the bigger level abstraction is the same for SONET and SDH, but between them there is a slight small difference. In India, for example, the equipments that we use in India would follow the SDH standards, whereas the same SDH standard will be understood by an equipment which is sitting in North America because of the interoperability. A corresponding standard which is based on packet switching is IP. We will talk about this a little later. Now, in the whole definitions of SONET and SDH, what is synchronous? We said synchronous optical network and synchronous digital hierarchy. Synchronous, we refer to the clock. So, all the clocks in the network are perfectly synchronized. In fact, it's very easy to synchronize with the GPS clock, or the clock is also transported and it's made available at every network node, right? Wherever you're dropping the channel, wherever you're adding the channel, or at all those locations where this framing is done, the clock is known so that you know exactly. So what exactly is a clock? It is a timing information. That timing information should be known to everyone. It should be common to everyone, because I cannot use follow my own clock and lag behind somebody else's clock, right? So the clocking has to be common. It has to be shared between all the different nodes. So all the clocks are perfectly synchronized. So then what happens is, when I say t equal to 0 in this node, that is the same, the way a node in, for example, Europe understands that is exactly at the same instant of time. There is no time lag, which means that when I am adding a specific packet or a frame here, I exactly know and where I am adding and what is being added, header, address, etc. The address, etc. is known in the header. So the receiver exactly knows that at, let's say, t equal to 0, I have added the transmitter, or this particular layer 2 has added that packet, and so it knows where to drop. Okay, so that is why it is called as synchronous. We had earlier way of there was an earlier standard called PDH, which is an asynchronous way where the clock is not really shared. In that case, it was becoming very difficult to create this multiplexing scenario to add data from different users who were operating at different data rates. So something called bit stuffing, etc. were used, but then this is not very commonly used anymore. So the current optical standard in the optical layer, the client layer standards are either SDH if you're outside America, or it is SONET. So what does the standard say? It says that, okay, so this is a picture that shows how this SONET layer lies. So you have the optical layer which has this O2E converters, and above that, and then you have the site layer which actually carries the, this is all optical fiber, but above that you have the SONET layer which has the add drop, ADM is add drop multiplexers. Remember, we are talking about electrical add drop multiplexing here. And this is where this is a layer, SDH layer, which is above this or rather a part of this optical layer, which will ensure that framing is done correctly and different users are multiplexed correctly. So what does the data rate of SDH or SONET mean? Of course, even though the names are different, the standardization is the same in terms of data rates, otherwise you cannot have interoperability. So the basic data rate of SONET is 51.84 Mbps, whereas the basic data rate of SDH is 155.52 Mbps, which means that you cannot really transmit anything which is lower than 155 Mbps. We should just ignore SONET, because whatever is we should start from data rates which are supported by SONET and SDH, which means that In an optical communication, the basic fundamental data rate that will work is only 152 Mbps. The standards allow a minimum data rate or the standards require a minimum data rate of 155.52 Mbps. Okay, so there's no 10 Mbps link or something unless you're doing it in your own point-to-point link where you're not trying to connect to a network. And that is referred to as either STM1, which is Synchronous Transport Module 1 in SDH standard, or in SONET standard it's called as STS3. STS indicates Synchronous Transport Signal. These are different names, but both of them essentially mean that there is a frame and this frame has data at the rate 155.52 Mbps. Okay, so this is the basic rate. STM4 would mean that this has increased by 4 times, right? So that has become 622 Mbps. STM16 would mean 16 times 155 Mbps. So that is 2.48832 Gbps, which is roughly what we are referring to as the 2.5 Gbps standard. The next standard is 10 Gbps. Then you have standard for 40 Gbps, then you have standard for 100 Gbps, and then you have the standard for 200 Gbps, right?